Okay, this is Machine Learning Essentials, Unit 1.4, and we're going to cover learning methods. Now, the previous unit talked about learning types. So we talked about supervised versus unsupervised, classification, and regression. And the next layer underneath those categories would be the methods that you would use for the actual learning process. Methods are used to identify, find useful patterns that you can then turn into models and apply to similar types of data. Now, in our world, there's hundreds of methods. And in fact, there's a whole book written about methods and the fact that maybe in the future there's going to be just one algorithm. This is pretty good by Pedro Domingos. He presents, I guess, in about a 400-page book, all of the different approaches and methods that are available and tries to give us the pros and cons of each. And the bottom line is it doesn't seem like there's a particular method or algorithm that is the best. It's more dependent on the use case that you're trying to address. And probably in the future, there will be one roll-up algorithm that can manage all use cases. But we find that sometimes we use different methods for different types of problems. So it's a pretty good book if you want to dive in deeper and take a look at all the different methods or what he calls algorithms that are available to the practitioner. Now this is the latest poll that I could find for what's being used in different industries as far as methods. And this is a pretty good website to go to. It's not just polling data, but it's a lot of informational stuff about machine learning and analytics. It's called kdnuggets.com. So this poll is showing us what the most popular methods are. I guess that was 4 years ago or so, and you can see that these methods here, like regression, decision trees, and even clustering, have been around for a really long time, and they're still being used quite a bit. So we're going to talk about regression and decision trees because we find that they work pretty well for the kinds of use cases that we're interested in. And then scanning on down through the list here, you can see random forests, which is really kind of a derivation of decision trees, is what we call bagging for decision trees. KNearest Neighbors, I got a pretty good example for that. Time series is just an algorithm set that looks at patterns over time. Ensemble, when you hear that word, that just means it's a collection of maybe many different types of algorithms. And here we got PCA, which is principal component analysis, and then boosting is also similar to decision trees. In this case, it's a whole bunch of trees in series. Then we have deep learning, and here's gradient boosted machines, repeated again, etc. So you can study all of these algorithms and get familiar with them, learn their pros and cons, if you will. You can just kind of look them up. But I thought I'd present to you just a few of the ones that we'll be looking at, we find it to be most useful for our kinds of use cases. The first is just simple classification and regression decision trees. Okay, so a simple decision tree looks like this, the top left. And this is a regression tree. So the way this works is you start off with your leaves that have records in them, and then this leaf will break up into its parts, and then further break up, and then further break up into another level. The practitioner has the ability to indicate how deep they want the tree to go, when to make a break or not make a break, and the number of minimum observations to include in each one of these nodes here. So we call these settings here hyperparameters. What I just mentioned, and decision trees have them. Some methods do not have parameters, but most of them do have something that the practitioner can employ to kind of get their model to work best for their particular situation. Down here on the right, I'm showing you what bagging and boosting looks like. And bagging would be for like random forest. This is where you're taking many trees and you're aggregating them all together. And there's some logic in here that rolls up all the trees into one decision type approach. Boosting would be where you're taking trees and you just string them in series. So decision trees have a lot of value in problem solving, and they're somewhat transparent too. You can kind of read them and figure out what's going on, within the black box. And as a point of note for decision trees, I just thought I'd show you how the leaves, how they break. So when you think about it, when uh, a decision tree is being constructed, at what point or for what predictor does it make that first break? Is it coding? Is it soil type? Is it CP values, et cetera, et cetera? And the way it can work, one way it can work, is through this information gain entropy change calculation. So from a practical standpoint, what's happening here? Imagine you've got a training data set with a whole bunch of records, whole bunch of observations in it, and it looks somewhat randomized. The question that the decision tree asks is what particular predictor is going to separate out and organize the data the best and reduce its entropy? So your current state might be this dot right here, knowing that here's your entropy scale on the y-axis. Okay. The and what this is showing is that, well, having an understanding of CP will give you this organization or reduction in entropy. It goes from this value to this value. Um, but it is also showing you that that coding type gives you the maximum organization, the maximum change in entropy. So the current state of randomness, if you want to call it that, of the learning data set might be here with this level of calculated entropy. And then if you bring coding in and start to separate out the data set into different coding types, then you end up with this calculation here of H entropy. And the actual entropy calculation is shown down here in the bottom. And if you're not familiar with Shannon's entropy law, this is a good thing to know. But you can run these probabilities through this log function, and you can actually calculate how much a particular predictor is going to reduce the entropy. So this is one way how decision trees make that decision of what predictor to break the tree into. Okay, linear regression, so moving away from trees. Linear regression is all about finding either a line fit or plane fit or some kind of hyperplane curved surface fit between observations. Okay, so that's all that's going on here. And just for visualization, I'm showing you a line, but you can see the line is being fit between these blue dots, which are the observations, and the best fit in this case is based on the ordinary least squares. So it's taking the residuals, so the blue versus the red line or this yellow point here. We make a box. That is your squared residual error. We add up all the squares, then take the square root of them divided by the number of observations, and we end up with RMSE, root mean squared error. And the algorithm, the fit, the way the math works is it's going to find the line that best fits with the lowest RMSE or lowest amount of error. And here's just kind of a discussion of the math behind it. We'll talk about that in another unit. But this is a real common approach, linear regression or multivariate linear regression. KNearest Neighbor is an interesting one. It's very simple. There's no parameters here other than the fact that you could set your K value. And what's unique about this algorithm is it all lives in memory. So it has to memorize the entire data set in order to make predictions. So let's say, for example, that you set your K equals 5, and you have here these red dots are known observations of defects. The green dots are no defect observations. Then you bring in this brand new point to predict, this yellow point. The question would be, what is this yellow point based on its proximity to these known points within this circle that includes just K equals 5 or 5 known points? And the answer would be green, which is no defect. And you can see we simply just say, well, 3 out of the 5 are green, 2 out of the 5 are red. So we're 60% confident that there's no defect here. I mean, that's how simple this algorithm really is, and it's used in a lot of different applications. Now, if you make our K bigger, then you end up with a different situation. So we draw a circle around our observations. And then you just simply count the reds, count the greens, and now this observation might be classified as a defect, because in this case, 7 of its 12 neighbors are defects, and 5 of them are no defects. So you've got a 58% confidence that this is a defect. So that's KNearest Neighbor. Another one is that's quite popular is Logistic Regression. I thought I'd mention this because this is a popular activation function algorithm for deep learning. So having an understanding of this will help you figure out deep learning techniques and methods. And this name is kind of misleading, logistic regression. You would think this is solving regression problems, but it's not. This is a classification method. So it's simply trying to figure out a best fit line based on this hypothesis over on number 1 here, where you get 1 divided by 1 plus e to the minus theta tx. And you can see the fit points here. And we're simply just trying to learn, this theta function. We're trying to learn this hypothesis based on these actual observations, and this becomes your model. So this is the actual learned model. And the predictions of whether it's yes or no, this is generally used for a 2-class kind of binary problem. Depends on where you fall, whether your new point falls, whether it's above or below this dotted line, the threshold. So you can see this yellow point right here. That's our point that we want to predict on. So we would predict this thing is true because it falls above the line, above the threshold on this fitted hypothesis. Now, deep learning is kind of interesting because this is an attempt to emulate partially how the brain works. And there's a lot that can be talked about this. You can really take a deep dive into deep learning and neural networks, but I thought I'd give you just kind of an overview. If you've never seen this before, it's really not as hard to understand as maybe it seems. So let's take a look at a use case that we all might be familiar with. Let's say we want to learn a model about external corrosion. And the way this would work is we start here on the left. Let's say we have some observations about coating, soil, CP, age, and power lines. And we also know when we see corrosion given these predictors. So we go back and take a look at a learning data set, an observation data set that has the list of when we see corrosion, when we don't see corrosion, and the individual predictors when they're present. Then we'll have an understanding of what we're feeding into this approach. So this first layer here, the input layer, would be the individual predictors. Okay. Then the next layer is going to be a hidden layer. And this hidden layer will then use an activation function. In many cases, the sigmoid function that we just talked about, but it uses an activation function to find out, well, what combination of all the inputs into one input, how can I weight those or relate those together to come up with a new derived engineered weighting that then humans can't understand. We can probably look at this, but it's not going to make a whole lot of sense to us because it's going to be a new predictor. Okay, and in this case, I'm just showing 4 points within the hidden layer, but you can have many layers to this. You can just keep adding more and more on, and these layers and these engineered features then become hybrids of what was previously feeding into it. But what you get out of this is, and this happens, very quickly. So this is all, computer speed. What you end up with is a collection then of features that are attempting, in this case, to predict yes or no for corrosion or a corrosion growth rate. You end up with an output layer that does make the predictions, and then the predictions are checked against the actual observation. So remember, we're feeding in actual observations, yes or no, or corrosion rates here. And this hidden layer is learning on those observations, but then when it pops out here, for every observation, the prediction, we're checking to see, well, how well did you do? How far off are you? And that's where back propagation comes into play, because that information, that signal is fed back to the hidden layer, and this process is activated again, where it says, "Oh, we didn't do a good job finding the a proper correct prediction. So let's go rerun this thing, and let's see if we can get closer." So it iterates through this process using different kinds of optimizers until you end up with a what we call a good prediction, something that would be acceptable to the practitioner. And you can see there's a lot of different types of neural networks, and this is an area that continues to expand and grow and advance, probably more significantly in voice recognition, text recognition, image recognition. Those are kind of like the three main areas where there's a lot of business need. Um, and for integrity and for asset management, we do leverage this as just another method we could pick and feed data in, set a few parameters, and let this thing run, and let's see what the performance looks like. So one last quote here is, I thought it's pretty good. You may have seen this with George Box. He's a quality control mathematician, that all models are wrong, but some models are useful. I thought I'd throw this in at the end to show you kind of what we were working with. Okay, so that's a real brief overview of methods. You have a lot of methods to choose from, and here's some guidance, like how do you go about picking a method? Well, sometimes it just depends on preference, what you're used to, what you studied, what you understand. Then would be performance. How well does that method perform? Are you getting the accuracy that you desire, the efficacy of the model? How about transparency? And you can see a decision tree might be a lot easier to explain to somebody versus a deep learning model. So that might be important. Then we get into explainability. So how do you explain the model, like the outputs out of the model? How can you justify and show that maybe a high prediction, like what it's made up of and why it is high? Then finally, just cost, because some of these methods can be quite computer expensive. Some are pretty cheap and pretty fast. So those are some considerations for picking the method that you want to use. I do want to mention that a learned model is a method purposed and tuned based on the learning data and objective, and we'll be covering this quite a bit, but that's the difference. The method is kind of like the pure hypothesis that we can just pull out of a package that's available to us, but it doesn't become the model until it's actually tuned and the hyperparameters are set, the coefficients are learned, and other information about the model is available to us. The basic machine learning process for all these methods are going to be the same, but there are some levels of complexity that are available to the practitioner. And I'd just say that the best approach is probably to master a few methods for your given collection of use cases and just get really good at those.